Okay. So before we continue, anyone has questions for the exam? Again, we can get back to this. But so y'all have started looking at it? Does it look easy? No? No response? People are not having this today? That's good if it's not super easy but doable. Ask questions in terms of I would gladly try to explain in the chat in Discord what if y'all have issues or questions and clarifications. Today will help. We'll basically answer some of the questions, reiterate some of the questions again. We looked at regression, but today, and I'm in a corny joke kind of mood, so today is about classification, right? Regression, the goal for us was predicting a number. We fit a line, for example. We tried to see, can we guess productivity score from doom scrolling? We wanted to do a number. And I jumped to the last slide. Okay, so we did a linear regression, which is basically the best line that could explain all those points. Today, we're looking at classification again with one of the algorithms. We've already looked at classification in an abstract, what it means. We're going to see how one of the main algorithms of classification work. So the question is not a productivity score, for example, is whether someone will join a subscription or not. That's like a general question a company might ask. You might do a trial campaign, and did that convert people to a paid plan, right? And then the next question is, then can we guess in the future with some of the existing data whether a user will convert to a paid plan or not, right? So now the question is, converted to paid is 1 or 0 or true false. That is what we're trying to predict, okay? Now let's go back to our scenario, similar as to your assignment. Let's say Figma gives every new sign up a 14-day free trial. We log how they use it, how much they use it at the end. Did they upgrade or not? Then the questions we can ask is, okay, is 14-day enough? Do we need to make it 30 days? Do we need to do other things? But it's good to say, okay, whether people converted or not, right? And how can we measure that? We can measure that by, okay, look at the number of trial hours used. We've logged that, how many hours each person have used, and we're plotting whether someone converted or not, right? So you can say, okay, this person converted and they had about 8 hours of trials used, and this person had 30 hours. This person used the tool for 20-something hours, but did not convert. Okay, so this is the outcome, and these are the values that we're looking at. So each dot is one trial user, trial hours is on the x-axis, and converted to paid is on the y-axis. We have only 2 possible outcomes. So now, do we fit a line to this? We certainly can, right? It doesn't make a difference. Like it for the computer, you can definitely fit a line. It would probably look something like this. But what you are predicting then is not like the thing that you like. It's not in the same format that you want it, right? There are negative probabilities because we want to say, okay, are we converting or not? What is the likelihood? What is the probability that someone will convert? Okay, so maybe a line is not a good idea. So what else can we do, right? We can do a different shape. We need something that stays between 0 and 1. Most classification problems, that's what you need to do because that fits our notions of probability that we learned. And it looks like something that's flat near the edges, steep in the middle, smooth everywhere. So if we can fit a line like this, then we can use it to make guesses. So we can squeeze any input into the range of 0 and 1. How do we read that? You say, okay, if the input is 25, then the output is close to 1. So if this is 1, this is 0. This is like 0.9, okay? And then we can say, okay, probability of converting is 0.9, something like that. It's basically probability of converted. That's how you read it. And then where the model is least sure, this is steep. Now, again, just so you've seen it, this is the logistic function based on the sigmoid curve. The idea is that you're trying to do the same linear combination. It's similar. So you're predicting an intercept, like I've shown you, and the slope of some line, but then you're squeezing it, right? So you're basically, this is a squeezing function. These are what we still have to fit, but then we do something with it. So this is called a sigmoid. It gives us a probability, not a yes, no, right? And to act on it, we need to cut off, like above this, predict converted, below this, predict not. Essentially, classification is still predicting a number, but the number is between 0 and 1. We think of it as a probability, and then we make an educated judgment. We say, okay, more than 0.5 probability, I'm going to say they will convert, okay? The cutoff, we use a cutoff, but we also remember that we don't have to use this cutoff. It could be any other thing, okay? So now this will be our decision boundary, right? So we can say, okay, in this curve, right, what is the trial hours used that gets the probability more than 50%, right? So what is this point? The boundary is a point. So we say 15.1 hours. If it's more than that, then we're going to predict that this is probability is more than 0.5. We're going to predict converted. If it's less than that, we're going to predict not converted, okay? This is our classification. This is how it works. This is the essential idea behind it, okay? This is our decision boundary. So where the curve crosses 0.5, then one number on the x-axis splits the whole space into two predictions. Everything to the right, predict converted. Everything to the left, predict not converted. And then the idea, how this is trained, again, just think in terms of intuition, is that not every curve is good, right? A lot of different sigmoid-shaped curves, right? Some are clearly better than the others. This is how we do. This is probably not a good fit. This is taking a lot of the curves. Now, this curve I drew is wrong. It should still be, the curve, I'll update it, but the curve should be like this, right? The curve I drew is wrong, but it's predicting everything as converted. Damn, every time I hit. Okay, this one is also not good. So it starts from here and then it just does this, right? This is the curve. And you can see that most is predicting most as not converted. So how do we decide? The idea is similar to fitting the least squares, but that's not what we're doing. We're not fitting the least square lines, right? What we're fitting, we want to find this best curve. How do we get the best one? We need a principled way. We're not just randomly checking. So this is what we call fitting the model, okay? And then the idea is that we don't also have to use 0.5. Lowering this threshold also moves the boundary. And we'll come back to this when we want to evaluate models. The way these models are trained, the logistic regression, is called maximum likelihood. The very idea is that for each user, the curve assigns a probability to what actually happened, okay? A good curve assigns high probability to what we observe. A bad curve is surprised by its own data. We want the curve that makes the data look as unsurprising as possible. So it gets all of these probabilities and then multiplies them together or sums them if it's logistic. You want to find the line that best explains all of these lines. That's called the maximum likelihood. The likelihood of seeing this data given this curve. What curve best explains the exact data that we have? right? So for example, this user barely used the app, but converted anyway. How do we explain this? So to do this, we get all of these probabilities and multiply every probability together. This product is the likelihood of the data, seeing the data given the curve that we have. We want to maximize this. So, and we use log likelihood. We take the log of that because it makes it more symmetric and easier because we can take the sum of them, right? The idea is that you have these now, you have these different curves, and then you want to find the maximum likelihood. Computer is going to do that for you. Just remember how it's doing it. We want to peak the maximum likelihood curve. For the linear regression, we're minimizing the error. Here, we're maximizing the likelihood of the data. Like most machine learning algorithms, it's just going to slowly look, find, do this, then change the curve somehow, and then find, come here, and then because the next one, it reduces, it knows to go back, and it will find this point. Okay. Now, how do we understand what those coefficients are? These values that we're creating. We say beta 0, beta 1 times x. What is this? What is coefficient of 0.2 to actually say about the world? You're going to have that in your assignment. You need to have a short detour through odds. We've learned what a probability is, okay? So assume that the orange dots are people who converted, and this is people who did not. The probability of conversion is the number of people who converted divided by total, all of this. So 7 divided by 10. The odds is 7. So the odds of conversion versus not converting is 7 divided by the other thing. Odd gives you how many times more likely is something to happen from the other one. Out of everyone, what fraction converted? For every person who didn't, how many did, essentially? Same information, different framing. And when we want to compare the two groups, we can look at the odds ratio. Odds ratio is the ratio of two odds. And then we have the ratio of odd ratios, which is a mind bender. The odds ratio is just one odds divided by the other. Here, heavy users have 16 times the odds of converting that of light users. So we take the odds here and get the odds here and divide them together. When someone says odds ratio is like 10, it means that it increases the odds. So just, you have to take these steps, and visualizing it in your head will help. So why do we use odds ratios? Because we want to use compare two groups of two values of a predictor, for example. Because it doesn't matter which outcome we call success, flip that label, or just becomes the reciprocal. So 116 here. This is exactly what you get, but exponentiating a logistic regression's coefficient. When we get that coefficient and do this, and you guys just did that, it's the bridge from models output to a real comparison. We had that example in the class. So a probability is a number between 0 and 1. Odds is from 0 to infinity, and log odds is symmetric because we want to look at it, the differences. We want the differences for reducing the odds and increasing the odds to be symmetrical. So negative numbers are reducing the odds, and positive numbers are increasing the odds. This is computing log odds directly. So we're fitting a line on log of the odds. And the sigmoid is a trip back from log odds to probability. So we fit a line that predicts the intercept with log odds, and then says, okay, this is the log odds times x, and predicts the probability of y, the log odds for y, and then we convert it back. All you need to remember is how to think about this, not how to calculate it for now. So the way you think about it is that what 1 more hour does to the odds of conversion. At low usage, probability barely moves, but odds still is times 125. At high usage, probability also barely moves, odds still 125. The coefficient acts on odds multiplicatively everywhere, not on probability. So the coefficient keeps multiplying and gets you the odds. Why this matters? Because when you say, okay, model.summary, it'll give you these numbers. This coefficient, trial hours used, it will give you a p-value, and then you will have the standard error and the z, because that's the coefficient plus standard error. So same 4 column you'll see for most logistic regressions. The coefficient and p-value are the two that you look at first. Everything else explains where these two come from. The idea of the p-value is that slope, is that thing that we're getting, just noise. But the idea is that shuffled is converted to paid across 300 users, same outcomes randomly assigned, and then build a model and calculate and then refit your model on the shuffle data and record the slope or record the coefficient. What is the likelihood? What is the probability of seeing this number if things were random? Remember, the p-value is just that. So for this case, like if the model was random, the coefficients would be like this. Ours is this. So we're saying we're pretty confident that this is a good coefficient. So this histogram is what no relationship looks like. 500 times by chance alone. P-value, fraction of the shuffles, at least this extreme. Here, it's actually 0 out of the 500. Again, most of these methods have like formulaic way of doing things, but simulation, I think, helps with thinking about them. Okay? And what the software actually does is uses another method. There are different methods for calculating the p-value. So you can basically divide the coefficient by the standard error. Again, I can share books if you're interested. I highly recommend the StatsQuest YouTube. It really explains things in a normal, simple way, but we don't have time. I just want you to be familiar with these things. It's the same logic as the shuffle test. It's based on some assumption, and you compare it to a normal curve. Okay? So just know that a p-value, if it's a larger number, then you're looking at slopes that are not meaningful. You might have two predictors, just like a line. Again, we're essentially building a line and then converted it to a curve, right? We can use promo emails sent, for example. That will be our second line. It will look like this on x-axis and y-axis. And what we want to do is we want to draw this line for now. It's a plane. You can't imagine it, but that will be your decision boundary. It's no longer a point, it's a line across the whole plane. And now this line is based on both of the coefficients that you're doing. Why? And then the other thing is that the promo emails really is not tilting it. So that probably means that it's not increasing the odds. And then the question is, we have more flexible models. In the assignment, you will have to go look at it. They're more complicated, so they can draw more complicated lines. They can bend, loop, and curve much more complicated shapes. And that doesn't mean it's automatically better. It might be able to memorize the data set that we're showing it. So what a logistic regression can draw a simple boundary and you can get a training accuracy of 66%, you might draw a line that gets a training accuracy of 92%, but then this might do really bad on new data because it's just memorized the training data. That's called overfitting. You will have to deal with that by sacrificing some complexity. So overfitting looks like this. Now, with two predictors, the coefficients look like this. Basically, the trial hours used barely moved from the single predictor fit. Without using the promo emails, this one is not as significant, right? It's the p-value is this. We're not really gonna interpret it. So a coefficient is not interpreted the way that we do with multiple regression. Holding the other predictor constant. So if we have not opened promo emails, how many times they have opened promo emails? If we don't change that, how does trial hours change affected? In plain language, an extra hour trial usage still multiplies the odds of converting by about the same amount, whether or not we also know promo email activity. So we might not get more information. In other words, promo email opened isn't adding any real predictive information once usage is already in the model. And sometimes these two things don't act independently. So we said, okay, how if we keep this constant and change that, what happens, assuming these two are independent, opening emails versus numbers of hours? We don't have to do that. Sometimes we think about interaction terms. This is more statistics, but you need to be able to understand what this means, right? So we basically engineer a feature that's essentially a multiplication of these. It has its own coefficient. What we say, does the jump change? That's a different question. 1 more hour of usage is worth a bigger jump in odds for heavy promo email users than for light ones. The difference is the interaction. I would like you to go back to the sentences and try to repeat it for yourself to gain the intuition for things like this. So the way you say is that for heavy users, 1 more hour of usage is worth a bigger jump in the odds for converting. So if they've got more promo emails, 1 more hour of usage, more probability of conversion. So again, so this is basically the additive model we've been fitting, right? When it's not 0, when this more than 0, right? We're gonna effect of x1 depends on x2, and symmetrically x2's effect depends on x1. How do we interpret it? It's not an odds ratio by itself. I showed you what an odds ratio is. Is how much the odds ratio per hour changes per extra promo email. So easiest to communicate by example, not formula. So odds type 1.15 for light users, odds time 1.46 for heavy users. That's the odds ratio. The catch is once an interaction is in the model, beta 1 and beta 2 stop meaning this predictor's effect. They now mean this predictor's effect when the other one is 0. And it would look like this when we add interaction terms. You have a bent boundary. Compare this, not wiggly, but you know that something is going on here. It's more interpretable complexity, not memorized noise. Okay. That's all I want you to remember from the idea of logistic regression, but you have to think in terms of odds when you talk about classification and looking at how predictors are affecting the outcomes. But another question is, again, in all data science, is our model good in terms of predicting the outcomes the way they should be? Okay, so remember accuracy, for example, 85% accuracy on our 20 users sounds good, but it's hiding something, right? Not every mistake is the same kind of mistake. A misconverter and a false alarm have very different costs in practice. So we have 4 ways of being right and wrong. We have true positives, true negatives, false positives, and false negatives. So we've looked at it in terms of a table, but remember, this curve is our model. So what are our false positives? These two, right? Because our model is predicted is here and is predicting if we give it this number, it's going to say they convert, right? So it's going to miscalculate these two, mispredict, misclassify. This is a false negative. This person actually converted. Our model is saying not converted. It's closer to this, okay? Think about these visually, helps a lot. So the true positive and true negative means that the model agrees with reality. The false positive, predicted converted, didn't actually. So it's a false alarm. False negative, predicted not converted, they actually did. It's a missed opportunity. Remember, in reality, these are based on a train test split. We have a training data, right? We train based on that and then use it on unseen data to create this chart. In terms of the confusion matrix, false negative, true positive, true negative, false positive. Same four categories laid out as a grid. The rows, what actually happens. Columns, what was predicted. Every classification metric is just some combination of these four numbers. So, what is accuracy? These are the things that you got right divided by everything. True positive, true negative, divided by everyone. So our accuracy is 85%. The diagonal, everything we got right. Now, this is everything that we converted as predicted. So we have converted, our model has predicted 9 people. So our model has predicted that 9 people will convert and 2 people will not convert. They've gotten 9 of it correctly and 2 incorrectly. That's our precision. Out of everything that we predicted will convert, how many did we correctly identify? Precision. We have been precise in our predictions. The things that we said, the people that we said they will convert, we were mostly right. That is our precision. Okay? 9 divided by 11, 82. But that's not the whole story. We also have, out of everyone who actually converted, how many did we get right? That's called recall. True positive divided by true positive and false negative. The sentence is, out of everyone that we predicted converted or we predicted true, how many were actually true? Here we're saying, out of everyone who were actually true or they actually converted, how many did we correctly? Yes, 90%. Of everyone who actually converted, how many did we catch? If you repeated it multiple times, you will get it right. So they have a trade-off. For example, in our model, we can catch more converters, right? The threshold was that number, 0.5, but more false alarms. Raising it, fewer false alarms, but you miss more real converters. In lecture 2, I think we've talked about this more. Here's a more rigid example in terms of logistic regression. Remember that this threshold of 0.5 is arbitrary, so we can choose it as 0.9, right? And then that 0.9 will give us a set of true positive, a rate of true positive, okay? And then here, it can get us a true positive rate that is higher. Here, it can give us another true positive rate versus false positive rate. Okay? In this space, every possible threshold is a point. Trace through all of them and you get a curve. This is a way to evaluate models. It's called the ROC curve, and then we get AUC. It's basically a true positive rate versus false positive rate across every threshold. Okay? So if we have really good true positive rate and 0 false positive rate, that's a perfect model. And the area underneath here is this number. That's what tells us the probability a random converter scores higher than a random non-converter. When AUC is more than 0.5, it means that we are not, is equal to 0.5, it means that we are no better than coin flipping. When it's 1, it means that we're perfect. So why do we do this? Because a single accuracy number depends on a threshold that we picked arbitrarily. With this, we can describe the model independent of any of these thresholds. It's useful for comparing models before deciding where to draw the lines. We can basically compare different models together. Especially valuable when classes are imbalanced, where accuracy alone can be badly misleading. So remember that wiggly boundary that we drew? 92% training accuracy for the wrong reasons. Regularization is the idea that we penalize the model for using large coefficients. So the model can still try to get complicated, it just has to pay for it. So we dial it down until we get better. It's just a concept of regularization. Same degree 6 polynomial features in all 3 panels, only the penalty changes. We get better models. More regularizations, simpler boundary, lower training accuracy, but far less nonsense. These are some extra information. Essentially, the L2 way penalizes the sum of squared coefficients, shrinks everything towards 0. The Lasso way to regularize it is the sum of absolute coefficients can push some coefficients to exactly 0, dropping features entirely. We're not going to deal with these, but I'll leave it here for you to know that these are important. So in C, in scikit-learn logistic regression is the inverse of regularization strength. Smaller C means more regularizations. Just remember that these exist. One might ask, what if there are more outcomes than just 2? That's a valid question. This is called a multi-class classification. So far, we're asking a binary question. Did they convert or not? 1 cutoff, 2 outcomes. The real picture is the trial user could end up churned. They might just stop using at all, or they might remain in free, or they can go in paid. So they might have 3 outcomes. We need probability for these 3 things that all sum to 1. It's what Softmax is. Essentially, each class, it gets its own scores in the model. Softmax turns the scores into probabilities. It gives us the probability of class K. In a lot of these newer models, LLMs, they're all using Softmax at the end. So this is how you get one number from a lot of different options. And that is Sigmoid's generalization. The idea is that you will draw 3 regions instead of 2 to classify. Same 2 predictors, now curving the plane into 3 zones. The regions meet cleanly. Every point belongs to exactly 1 class. This is a classification based on reading coefficients with 3 plus classes. The model picks 1 class as a reference. Every other class gets its own coefficients, interpreted relative to that reference. So is a relative risk ratio. How much more likely that class is than the reference per unit increase. Not quite the same as a binary odds ratio. Again, this is not something that we're going to work with, but remember that it's a problem that you're going to have to think about when you do multi-class. How do we do it? For logistic regression, we can think about 1 versus rest. So we can, every time we can say, okay, churned versus everything else, paid versus everything else. So we can build 3 logistic regressions, or we can use Softmax. So we can create a specific type of logistic regression that actually predicts the 3 classes using multinomial, and then we can just use Softmax to get the probabilities. We've now looked at classification and regression, the very basic models. In the next sessions, we're going to do unsupervised learning, and then we're going to get much more software like data science, like in practice. But these are the basics that you need to know, right? Probability output is important. Decision boundary is important. Confusion matrix is important. Go look up ROC or AUC. These are applies to any classifier, not just logistic regression. What changes between models is how the boundary gets drawn and what's being fit. So we'll have new vocabulary by family. We'll have decision trees, which splits different parts and then just goes on, and we use entropy to fit it. There's no coefficients, just which question to ask next. We have k nearest neighbors. We want to look at the distance k. There's no real fitting, just memorize and compare. You can use ensembles, which is basically maybe a bunch of different decision trees, different types of ensembles, baggings and boosting. Combine many simple models, hyperparameters like numbers of trees and learning rates. If you go take a machine learning class, you will have to deal with this. Support vector machines. You want to find the margin that minimizes the distance between the, it's hard to explain it in English, but it's about finding the margin between two classes. All I would say is that you can look at these, and a lot of these things that you learned applies. In your assignment, I want you to go look at one of these and then try to build it. The other things that you want to know is hyperparameter. Hyperparameters are things that parameters are learned. These are like the coefficients. Hyperparameters are chosen by you. For example, how many leaves for a tree do we use? Most of these models, they do not have a solution. We do an iterative search, and just like this likelihood hill that we climbed earlier. Cross-validation becomes essential once there are hyperparameters to choose from. That's all we want to do with classification. We're going to do another sort of more complicated classification, but from now on, I think your task is mostly to try to, for now, unless you want to take like a complete machine learning class or statistics class, the goal is for you to be able to understand these large amounts of vocabulary. I just dumped a bunch of vocabulary on you. Don't be afraid of them. Go look at a video, say, okay, how does support vector machine work, or how does an LLM work? A lot of the ideas come from the same thing. Softmax is in an LLM. Linear regression is in an LLM. All of these are built towards each other, okay? But we're not going to cover it. The AI class covers some other parts of it that Nilay teaches. Do we have any questions? So that was the last, this is the last session where we have math and stuff. If you're bored, I know y'all, a lot of you are designers, try to learn these. I hated them, but ended up being really useful for me. So take it as it may. There are some more math, but any other questions? I can stop recording and I can stay on a couple more minutes if y'all want to ask questions about the exam. I will post this video tomorrow morning.